Well, let's talk about linear combinations of vectors. We've already talked a little bit about linear combinations of rows in a matrix, and this is going to be similar. So let's talk about it informally first. We'll get to the formal definition later. But for now, let's just look at this. If we take a bunch of vectors from Rn and multiply them by some scalars and add them up, the resulting vector is a linear combination of them. So the only reason I'm saying from Rn is because we've got to make sure that the vectors are all the same size so we can actually add them together. So let's look at this example. Suppose that u1, u2, and u3 are these guys. Then if we just take any coefficients, and I just randomly picked 2, -1, and 10. If we take these coefficients, multiply them by these guys, we're going to get some resulting vector that's a linear combination of them. So let's add this one up. So the top entry here is going to be, let's see, 2 times 3 is 6, minus 1 is 5, plus 10 times 4 is 45. Okay, this next one's easy because it's 2 times 0 minus 0 plus 10 times 0. So that's just 0. And the last one is, let's see, 2 times 2 is 4, minus 8 is -4, plus 90 is 86. So you get 45, 0, 86. And that's a linear combination of those three things. So that's just one linear combination. There are infinitely many of them. So let's look at this question here. Is 147 a linear combination of these three vectors? And this one we can actually do without having to really do much work. And it's because these first three vectors are chosen with the 0 in the middle. So if you add these three vectors up, multiples of them, there's no way you can get something that's non-zero in the middle. So the answer to this is no. And we'll come back to this a little later and see another way to tell that it's no. But for right now, let's think about this geometrically. I'm going to draw some axes here. Three-dimensional axes. I never can remember the right convention for this. Different people use different things. I'm going to call this X, this Y, and this Z. If you look at these three vectors up here, all of them have a 0 in the middle, so their Y component is 0. So if we were to draw these in the plane, all of them would be trapped, or they'd all live in the the XZ plane. So they'd all be over here. You'd have 302, 108, and 409. They'd all live in there. And then this vector here, 147, if we were to plot that, its x-coordinate would be 1, its y-coordinate would be 4, and its z-coordinate would be 7. Now, the way I plot these is I sort of go along each dimension. So x would be 1, y would be 4 steps parallel to the y-axis, and then 7 steps parallel to the z-axis. So we're looking at a vector that points up there, and that's outside of the xz plane. So yeah, there's no way you can get that from adding up vectors that all are stuck inside of here, whatever they look like. All right. What about this next one? Is 4, 5 a linear combination of 1, -1, and -3, 3? This is another one we can do by sort of analyzing the picture. The vector 1, -1 is going to be something like this. It's going to point in that direction. Then -3, 3 is going to point in the exact opposite direction. And if you start thinking about multiplying these by scalars and adding them together, all that's going to do is multiplying by scalars is going to stretch them or compress them, but they're still going to be trapped on this line. And when you add them together, you're also going to be trapped on this line right here. So there's no way to add multiples of these guys together and get something that's not on the line. And 4, 5, let's see, go over 4 and then up 5. 4, 5 over here. There's no way you can get that by adding multiples of this green and blue vector together. So the answer here is also no. So tell you what, let's do. Let's do this instead of just looking at it and analyzing the pictures. How would we do this if we how would we do this using algebra? Here's what you do. If you're trying to decide if this is a linear combination of these guys, what you do is you just set it up as a linear combination. I'm gonna erase my picture so that I have space here. So what you do is you just set up coefficient times the first vector plus the coefficient times the second vector equals 4, 5. And you have to solve this for C1 and C2. Now, you could rewrite this if you wanted to as a system of equations. That'd be C1 minus 3, C2 equals 4. And this would be C1 times negative 1 plus 3C2 equals 5. And so we need to solve this. Now, this is not a hard one to solve, but I'm going to write it as a matrix and solve it with octave. Reason being is that's what we're going to do in general. Most of the examples aren't going to be this small. So write it as a matrix. When you take this and row reduce it, let's see. Yep, that's a preview from an upcoming problem. Get that out of here. I'm going to call this matrix N. Let's see, we've got 1, negative 3, 4, then negative 1, 3, 5. And when you row reduce this, you get this 0, 0, 1. So that tells us that we have, I'm not going to even copy the rest of the matrix because that's the important bit. That right there says there's no solution. And if there's no solution, that means there's no C1 and C2 that work for this. So therefore, it's not a linear combination. Let's look at this next example. Is this thing a linear combination of these? And that's not one. I mean, this is in 4-dimensional space, and that's not something you can just look at and tell the answer to. So we do the same thing here. We'd set up, I'm going to write it up here just to save some time. You do C1, actually no, I'm going to write it out. You do C1 times 1, 3, 4, 2 plus C2 times negative 2, 1, negative 2, 1 plus C3 times 4, 4 minus 1, minus 1 equals minus 9, 9, 5, 9. So you've got to solve this system. And again, the way to do this is write it as an augmented matrix. And then we're going to row reduce it. So let's use octave to do that. And at this point, notice really all we're asking is this a linear combination? So we're really just looking, does it have a solution or not? So let's do this on octave. Now I typed this one in earlier, but I think I made a mistake on it. Yeah, that top line, that should be a negative 9. And actually I've got a mistake over here. This should not be a negative there. So let's just double check that those columns match up with the vectors we've gotten. Yeah, that's good. So if we take the reduced row echelon form of N, oh wait, reduced echelon form of m, we get this. And this down here is bad news. Well, it's not bad news. It just means the answer is no. Again, let me double check those columns, because I thought the answer was going to be yes. 1, 3, 4, 2, minus 2, 1, minus 2, 1, 4, 4. Okay, no, that's correct. You row reduce this thing, and we get a 0 equals 1 on the bottom. So the answer here is, again, no. All right, we'll look at the formal definition in the next video.